Hi there, in this video clip I want to talk about endothermic and exothermic reactions. Exo means outside, endo inside. Exothermic reactions are reactions which give out heat, and endothermic are reactions which take in heat. So exothermic, things like reactions such as explosions. If I took a fuel and I burn it in oxygen, for example, if I took methane gas, CH4, and burn it in oxygen, it gives me carbon dioxide and water. It's an exothermic reaction. And if I take an acid and an alkali, which gives me a salt and water, it's an exothermic reaction. I can actually feel them getting hot. And if I burn a log on a fire, it gives out energy in the form of heat. It's an exothermic reaction. The opposite of exothermic reactions are endothermic reactions, and these are reactions that take in heat. Where did he take it from? The atmosphere, i.e. if I got an exothermic reaction, I get an increase in temperature, and if I get an endothermic reactions, I get a decrease in temperature. You know, you get those ice packs, you break them, you put them on your feet or whatever, and they get cold. That's an example of an endothermic reaction, as opposed to you can buy these hand warmers, chemical jobbies. You bend them a couple of times and they get hot, and you stick it on your hands or in your boots if you're hiking to get warm, and that is an example of a exothermic reaction. Let's look at the reaction profile. And here is profile 1 and here is profile 2. Let's look at an exothermic reaction. There's the reactants, and let me change that diagram. There's the energy of the reactants, there's the energy of the products. This it's a time, it's, as time goes on, what happens to the energy. There's the energy, there's the energy of the reactants, and there's the energy of the products. So the energy of the products is less than that of the reactants, and therefore it gives out energy in the form of heat. And let's take the converse. If I took something like the reactants here, and there's the products there, that difference is absorbing energy from the surroundings. So that is the difference between an exothermic and an endothermic reaction. If that's the energy and the product's energy is lower, where's it gone to? The energy it's given out. The converse applies to endothermic. There's the reactants, there's the products at a higher energy. Where's that come from? It's taken it from the surroundings. Now, those energy changes, there's a bit more to them involved than that, right? So what happens, for example, if I took methane, CH4, H, and it's burnt in oxygen, it forms carbon dioxide and water. What happens is, you can see there that some of those bonds get broken. They break. The energy that keeps those bonds together is called the bond energy. So in the case of that, bonds are being broken, and here is oxygen, and those bonds are being broken. Whereas here we formed bonds between the carbon and the oxygen, and we formed bonds between the hydrogen and the oxygen. Therefore, this is a typical exothermic reaction in which, when bonds are broken, energy is released, and when bonds are formed, the energy is gained. And the final thing I want to speak about is the concept of the activation energy. Let's take a couple of reactants, A and B, reacting with C and D. They don't just react. The atoms, the molecules, they have to have a certain amount of energy to start with, to kickstart that reaction. If I took something like a log of wood and I've got a match, I know this, eventually that log will burn, burst into flame, and it will go on and on and on. However, if I took that match, it's not sufficient to make it start to chemically react with the oxygen. And we have to supply, or there's got to be a certain amount of energy before these molecules get sufficiently excited to collide and hit each other before the reaction occurs. And that is the concept of the activation energy. So if I took something like this, there's the reactants, and here's the, let me change that. There's the reactants and there's the products. What happens is I have to kickstart it with a certain amount of energy, and that amount of energy is the activation energy. Don't forget, this was the time or the extent of the reaction, and this was the energy. So the amount of energy I have to apply to start off a reaction, once it starts, it continues, but that is called the activation energy, and let's just, for sake of it, call it dA. And if I took the same diagram, but let's call it the reaction profile, there is the reactants. I've cocked that up. There's the reactants, there's the products. I have to supply a certain amount of energy, the activation energy, EA. There's the reactants, there's the products. And that is the reaction profile for an endothermic reaction, which are reactions in which energy is taken from the surroundings. Now, I've said in exothermic reactions bonds are broken, and in endothermic bonds are formed. Let's look at an actual example. Next, I've got hydrogen reacts with oxygen to form water, 2H2O. Let's look at the bonds in this, and the bonds in this, and the bonds in this. The bond energy, the energy that is required to break bonds. So let's take that. I've got H and H, and I've got H and H, and here I've got O and O, and here I've got OH, and I've got OH, and I've got H2, and I got H and H. Now, let's look at the calculation of the bond energies of the reactants with the products. Okay, this is exactly what I've got. I've got H, 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 H. H, the bond energy of hydrogen to hydrogen, is 436 kilojoules. That's 436 kilojoules. Oxygen, the bond energy between the O and the O is, it's a bit more, it's 496. And going back to that, I've now got OH, OH, hello, I've made a mistake.